Imagine if there was a way to tell how big an eruption was just by looking at the ash cloud. Turns out that there is. A little over 10 years ago, scientists put forward a new proposal for classifying the size of ancient eruptions called the Volcanic Explosivity Index, or the VEI. This system helps answer a question that's been plaguing humanity since we first looked up at the sky and saw a mushroom cloud, which was the biggest one. We have some ideas about that, but it's hard to compare eruptions that happened hundreds or thousands of years apart because chances are pretty slim that we're going to find good records about them from back then. And even if we do, different observers might have had different ideas about what they were seeing. So we need something based on the science to help us make sense of all these stories, and something that can help us judge the size of eruptions that left no written record at all. And while the VEI isn't perfect, it's the best tool we've got to unearth history's biggest blasts. First off, let me level set with you. Just because something's called an index doesn't mean it's like an index card. The VEI is actually more like a set of guidelines. It categorizes volcanic eruptions into 8 categories ranging from 0 to 7, where 0 means there's no eruption at all, and 7 means total annihilation. Or maybe not total annihilation, but definitely a really big explosion. The trouble is, there's no single thing that links all of these categories together. In fact, there are 5 different ones in the VEI. If you want to know the VEI of an eruption, you have to consider 5 different things: the volume of ash and rock ejected, the height of the ash cloud, the width of the ash cloud at its base, the duration of the eruption, and the Volcanic Explosivity Index. These 5 factors are all related to the size of an eruption, and they all contribute to the overall VEI rating. But there's a lot of wiggle room in how exactly you connect those pieces together. Take Mount Pinatubo, for example. When it erupted in 1991, the world got a live demonstration of how devastating a large eruption can be. But the VEI rating for that eruption wasn't determined by any sort of committee of volcanologists watching the news coverage that weekend. Instead, scientists compared the observed features of the eruption to well-studied ancient eruptions, particularly the 1815 eruption of Mount Tambora in Indonesia. Scientists determined that Pinatubo's ash plume reached a similar height as Tambora's and that its ejected material was about the same volume. Because of that, Pinatubo and Tambora both have a VEI of 6. This kind of comparison is a pretty common way to figure out the VEI of an ancient eruption. You find one that seems pretty similar in the geologic record and give it the same VEI, and sometimes that's all you can do. For example, the oldest known eruption of Mount Vesuvius, the volcano that destroyed the Roman city of Pompeii in 79 AD, has a VEI of 5. Mostly because it seems comparable to other eruptions in the region that scientists have studied in detail. But if you're dealing with an eruption that's totally unknown outside of the historical record, say an eruption mentioned in Egyptian writings from 3,200 years ago, the VEI guidelines help you piece together what the eruption might have been like. Take the Egyptian eruption, for example. The writings say that the sun turned into night, which could suggest that the eruption plume blocked out the sunlight. Depending on how dark it got and how long it lasted, that could point to a VEI between 4 and 6. If the writings also say that people could see glowing fragments of rock raining down from the sky, that would suggest a pyroclastic flow. These hot mixtures of rock, ash, and gas rush down the side of a volcano during an eruption and can travel at speeds over 100 miles per hour. If the pyroclastic flows traveled far beyond the volcano, maybe destroying entire towns along the way, this eruption might have had a VEI of 5 or higher. But if the glowing rocks only made it a short distance down the volcano's slopes, then the VEI might have been lower. Each piece of information like this is considered individually and combined together with all the other evidence we might have about an eruption to estimate the VEI. That being said, there's still a fair bit of uncertainty about the details of any eruption that didn't leave behind any physical evidence. So in the end, it's possible that this Egyptian eruption was anywhere from a VEI of 3 to 6. And while that's a range of 3 whole points, keep in mind that each point on the VEI represents a 10x difference in explosive power. A VEI-3 eruption is 10 times more powerful than a VEI-2. A VEI-4 eruption is 10 times more powerful than a VEI-3, and so on and so forth. So if you're trying to figure out which eruption in history was the biggest, it helps to get as precise an estimate as you can. One reason why we want to know the exact VEI of an eruption is that it gives us a better idea of how much CO2 was released during the eruption. This is important for understanding how a specific eruption affected the climate, and also for understanding how future eruptions might affect our planet's climate. One team of researchers used the VEI and other data to estimate the amount of carbon dioxide released by the 10 largest eruptions of the past 13,000 years. They found that these 10 eruptions released roughly 2,800 gigatons of CO2. For context, human emissions are somewhere around 3 gigatons of CO2 per year. And to keep the party going, the researchers estimated that it would take about 1,500 years of emissions at this rate to match the carbon waste produced by these 10 volcanoes alone. Unfortunately, there's a limit to how precise you can get with the VEI because of the way it was designed. Remember how I said that there are 8 categories, and each category represents a 10x increase in explosive power? Well, the last 3 of those categories are pretty rare. Only 12 eruptions in the past 13,000 years had a VEI of 6 or higher, and only one of them broke into the highest category, VEI 7. That's the 1815 eruption of Mount Tambora. Since the VEI is a logarithmic scale, having only one eruption in the top category means that there's a huge gap between the second and third most powerful categories. It's like saying if you run a mile in under 6 minutes, you're a great runner, but if you run it in 6.01 minutes, you're only okay. Now, maybe that's fair because 6 minutes is really fast, but the problem is the VEI compares the largest eruptions ever recorded with the smallest ones. So the biggest eruptions of the past 13,000 years are grouped together with eruptions that are 10,000 times less powerful. On top of that, eruptions that are close together on the VEI can look vastly different. At a VEI of 3, an eruption might send an ash plume 3 kilometers up into the air and eject 100,000 cubic meters of ash. A VEI 4 eruption might shoot ash 10 kilometers up and eject 1 million cubic meters. Meanwhile, a VEI 5 eruption sends ash 100 kilometers up and ejects 100 million cubic meters. Those all sound pretty similar except for the heights, but they differ by orders of magnitude when it comes to the volume of ash ejected. In fact, you could have an eruption that sends ash 100 kilometers up and only ejects 10,000 cubic meters of ash, which would fall into the same category as the other 3 examples. But there isn't any way to account for this in the VEI. So it's unsurprising that there have been proposals for new, improved versions of it. Some scientists would like to replace the VEI with a formula that uses the volume of material ejected as the main factor for determining the explosivity. Others want to use machine learning algorithms to analyze lots of data about an eruption, such as the volume of material, the height of the ash plume, and the shape of the ash cloud. Then an algorithm can spit out a number that takes all of these pieces of information into account. Ultimately, the goal of these new systems is to give us a better idea of how big an eruption was and what effects it might have had. Of course, we don't need to change the VEI to realize that human activity makes giant eruptions more likely. You can learn more about how humans are driving volcanoes to blow their tops through the link below. Thanks for watching this episode of SCI Show, and thank you to one of our patrons for asking this question. Our patrons could submit questions to our inbox, and our editors pick out the best ones to answer in episodes like this one. So if you've ever wondered how something works or why something happens, you can get your answers at our website.